Okay, so now let's work an example using Ohm's law for AC circuits. Here we have a voltage source with value V of t equals 170 cosine 120 pi t is connected to a 240 ohm resistive load. What we want to do is determine the time domain equation for the current through the load. So if we've been given an AC signal and it's connected to a purely resistive circuit, then let's determine the current through it. So let's just draw a circuit model to start with. We've got a voltage source, V of t. We've got a resistor. It's connected directly to the terminals of the voltage source, so we say that that is in parallel. This is 240 ohms, you'll recall. And our challenge is just, can we find I of t? So what we're going to do is we're going to use Ohm's law written for AC resistances. So we get Vm, max voltage, cosine of omega t, plus the phase shift, V sub V, equals the resistance times the max current, cosine of omega t plus the phase shift of the current. So we can plug in some numbers here, and we get 170 cosine of 120 pi. That was given to us in the problem. There is no phase shift. We then equate that equal to R, and we just need to multiply that by I of t. And so we can just divide. We get I of t is then equal to, R was 240 ohms. So that'll be 170 cosine of 120 pi t volts. We divide that by 240 ohms. And what does that give us? That gives us a I of t equals 0.71. Cosine of 120 pi t. And that's measured in amps. So we had a purely resistive load of 240 ohms. We applied a sinusoidal voltage to it in the form of a cosine wave, and we see that, again, resistance, it only has an effect on the amplitude, which was 0.71 amps. It did not affect the shape of the waveform, or the timing information of the waveform. The frequency, the angular frequency, 120 pi radians per second, remained the same, and the phase shift, which in this case was a 0, remained the same. So what you need to remember about resistance, it follows Ohm's law for both AC and DC. In the AC form, it has no effect on the timing information whatsoever.